All right, 20 people, do we start? You're ready, Thibault?
Oh, all good.
Okay, welcome everyone. It's my pleasure to have Thibault Pirson from UC Louvain here today giving a talk. Title of the talk is Why Do We Need Lifecycle Thinking in the IoT? So it's a bit more of a sustainability topic that we are talking about. I know Thibault for maybe 2-3 years already, so we've been organizing the SICT Summer School for Sustainable ICT together, and I'm really excited to have a cool publication from their group being presented here in our seminar series. Looking forward to hear what you have to say, Thibault. If you have questions, if you want to discuss, unmute your mic or raise your hand or put your questions in the chat. We're gonna moderate this afterwards, and I'm looking forward to a great discussion with everyone. Thibault, the floor is yours.
Cool, can you hear me? Yeah, great. Thanks a lot, Jan Tobias. So yeah, indeed, the title of the presentation is Why Do We Need Lifecycle Thinking in the context of the IoT, so Internet of Things for the ones that are not familiar with this this term. And I'm Thibault, so PhD student at UC Louvain, as you properly introduced me, Jan Tobias. I would like also to thank you for inviting me for giving this talk. It's a nice opportunity to share and as always collect also feedbacks and people that are aware, not aware, and pushing these topics further. So let's first start by a small introduction. I would say that I think we all agree on the fact that ICT, so ICT stands for Information and Communication Technology. These are really useful. We use them to, as you can see here, to like communicate, make business, share, compute, relax, play games, a lot of things, and all of this is made possible by a big infrastructure which gathers smartphones, TVs, access networks, data centers. So it's a big infrastructure, but it is really, really useful, and I think we quite all agree on this. However, at the same time, we are also facing a climate crisis, as many people are aware now. It is usually people usually focused a lot on GHG emissions and carbon footprint. And as we can see on the left side here, it's also often presented as the need for a sharp decrease of the GHG emissions or up to 2050, which is not at all the trend that we are seeing so far. But there are also other issues which are more related to like biodiversity collapse and the impact and the stresses that we introduce as humans on the ecosystems. So all this, I think you kind of know that, but I would really stress the fact that the point here is that we are facing a huge challenge. Why? Because we have really a few trials to get that shift right, and a very short period of time, which is really important to stress again, because it means that today's action are really critical for the future, upcoming future. And as we are working on the ICT topic, it begins really interesting to kind of understand what is the footprint, at least the carbon footprint of ICT footprint. And there are a few studies on that, not only one, but I would say that they all agree on something, which is that terminals are the main hotspots for the carbon footprint, and then network and data centers, sometimes one before the other, but still it's roughly, they roughly agree on that. It's really the terminals that are the main hotspots of this carbon footprint, mainly because of their numbers. And as you can see also on this pie chart, the production is not the biggest part of the carbon footprint, but still significant, and the rest is for the use. Also, it is interesting to see, either with absolute number or relative numbers, that it represents roughly 6 to 7% of the annual electricity energy worldwide. And regarding GHG emissions, it's about like 3 or 4%. So what we could conclude directly is that it is not the main hotspot. It is clearly not 50% of GHG emission. And so we could ask the question, so why is it necessary to dig deeper in this question, and why do we need to monitor this ICT carbon footprint? I would say that the answer is that when we look at the future trends, scientific literature is does not agree. Some are saying that it's increasing, some others say that it's stable or decreasing. And so even though they agree on the current situation, the future trends are not at all clear. And as Paris Agreement also calls everything to decrease by 2050, we could also ask the question, we need to make ICT footprint decrease as well. And the point that I would like to make here is that all of this does not include the carbon footprint of IoT. And when we look about a few numbers regarding IoT, so the Internet of Things, we see that it's probably one of the main and one of the fastest growing trends occurring in the ICT. As you can see here from numbers by Cisco, the number of devices is really expected to increase quite fast. So here in blue, you see machine-to-machine, which is also called sometimes IoT share, which is really the reason why it keeps increasing here. And if we take a step back from Cisco and we compare with other trends that are acknowledged, or at least that are mentioned in the literature, we see that Cisco here, it's the green line, is really, I would say, an optimistic trend regarding the number of devices. We saw that other studies expect a higher number of devices. And so a quite natural question that can come into the discussion is, what about the environmental impacts of a massive deployment of IoT devices? Because that's what we are talking about at the moment. And when we are talking about environmental impacts, we are not just talking about the use case. So let's say, okay, we deploy this IoT application, and then we see how it goes during the use phase. Here, it's really about a mindset which covers the whole life cycle. We call that mindset, we could say, life cycle thinking. It's really that way to trying to consider the impacts, not only from the use phase, but really from all other phases of the life cycle of a device or services. And this is supported by a well-known methodology, which is called life cycle assessment, which is an ISO certified methodology, which support that modeling from the raw material extraction to production, transport, use phase, and finally the end of life and the disposal of the devices. And here we are back to the title of the presentation. Why do we need lifecycle thinking in the context of IoT? And that's really what I would like to discuss with you and to dig further in this presentation. What I'm going to talk about, it's mainly two research work that we did over the past month. Specifically on modeling the environmental impacts of the IoT devices. So the first study is the carbon footprint of IoT production. And the second one is more a very specific use case on wireless power transfer. So that you know a bit what we are going to cover in this presentation. A few conclusions and perspectives. And obviously I will try to not be too long, to have also time for open discussions and Q&A, obviously. If during the presentation you have something that you do not understand or something that is not clear, please just open your mic and ask the question. So here we go. The first part is LCA of IoT. Back to this, I would say, schematic representation of the ICT infrastructure, in which we added the part for IoT. So here you see traditional connected device, which are what you know, like PC, TVs, computer, things that are commonly discussed in the ICT infrastructure. IIoT, which stands for industrial IoT, and everything which is connected to like IoT within the industry. And this is like IoT for consumer, I would say, and so either battery powered or main powered. Here, the gateway that made possible the connection to the access network, which is a common part of the ICT infrastructure, either mobile access or fixed access. And then we have everything related to like edge network, core network with switches and routers, edge data centers, and finally at the end, the cloud and data center, and the data is going this way back and forth. So this is for the structure of the I would say the schematic here of the infrastructure. It is important to keep that picture in mind because we will come back a few times to it. On the right here, we have the life cycle that we see earlier, okay, with the raw material extraction and the different phases of the life cycle, and here the indicators. And I just using this to make really clear the scope of the study, because it's really important to understand on what we are discussing and what has been included or not in the study. And so here you see that the study that we are talking about now is really focusing on the IoT part here, not the industrial IoT one, really IoT, I would say more consumer-like. For the life cycle phases, it's only production and transport, raw material as well, but so not the use phase and the end of life. And the only indicator that we consider is the global warming potential, which is also like the carbon footprint. A big challenge in the IoT is so to define the environmental impacts, but the question that we ask in this paper is how can we model the embodied carbon footprint for a wide range of IoT edge devices while preserving precision? Alors, it could sound weird that way, but a big challenge in IoT is that there are so many different IoT devices that it is really hard to have if you do the LCA for one specific IoT device, when someone else comes with another IoT device, it could be really different from the one that you evaluate the environmental impacts, and so really difficult to compare. As we spotted that big gap, we said, okay, it's not interesting, at least this does not answer the question if we focus on a specific device. And so let's try to find a way to model the carbon footprint of a wider range of IoT device, but still try to keep the precision in the way you are doing the life cycle assessment. And we come up with the idea of splitting the IoT edge device in sub-blocks that are blocks very often used for the different devices. And for each block, we split it in different levels, so that we call hardware specification level, different level of hardware that can define the IoT devices. I will come up with more precision the slide just after. But the idea behind that is that if we have this split in different blocks, we can then use what we call Iot hardware profile. And so taking a specific IoT device, looking at the closest match in the framework that we proposed, and then obtaining the resulting carbon footprint. So this is the idea that we propose in that paper and that we implement as well So I will go more into details now. It's completely normal that you cannot read the table. It's not the purpose of it. I just want to explain the structure, and we will zoom just on one sub-blocks here. So in the table that is there, this is basically the specific details of what we considered for each block in the framework. So here on the left, you have all the blocks that we have defined here. So actuators, sensing, connectivity, etc. Here on the left. And here on the right, you have the different levels that we defined for each block. And so if we take this example, for example, this is the block others, and the hardware specification level is the level 2. We see that we define how many capacitors, resistors, diodes, transistors, what cables are considered, etc. With a low, typical, and high value. And we do that for every level, for every block, which yields a high transparency on what is considered. This definition of the different level and blocks has been based on data sheets, review of literature, reports, tear down that we also carried out in labs, and expertises of the group, because the group in which I'm working, and which is led by David Boll, is the group of electronic and circuit and systems at UC Louvain. And so we have one part which is focusing more on the environmental impacts, but another part which is actually developing ultra-low power chips, and which has a big expertise in system and integration, which really can fuel the discussion and the research about the modeling of impacts. So obviously this is not exhaustive, but it already covers a wide range of IoT hardware. And there are a few gaps that are mentioned here that we can discuss later on, but that I will skip for now. Again, you cannot read what is on the pictures. This is completely normal. What I want to highlight in this slide is the process. On the left, when we defined the different blocks and the different level, then we modeled all of this in a LCA tool, which is called Gabi from the society Sphera, which is a LCA tool and also electronic databases, so a database explicitly for electronic. And then we modeled all these different blocks and hardware specification level to finally obtain the result for each block in carbon footprint, the result of the carbon footprint. If we zoom on this result, what we see, so it's a log scale. We provide results for each block and each specification level in order for the framework to be easily reused in other studies or other people that would like to have insight on the carbon footprint of IoT devices. So this is really an objective of this footprint. But also what we can observe is that as we have the result here for a wide range of devices, from very simple device to very complex device, we can also see that the carbon footprint varies quite a lot, from a factor of more than 150 between very simple and very complex devices. So the point here is really to highlight that you cannot just do like average and say, okay, all IoT devices will have that carbon footprint. This does not work like this. For example, for smartphones, it's easier because smartphones are more similar, and so there is less variability in the result that you have for the carbon footprint. If we go a bit one step further, when we finish the framework, we then say, okay, let's apply it on 4 use cases that are actually one occupancy sensor for room monitoring, a smartwatch, a home connected assistant from Google Home, and the fourth one is a drone from Mavic. We try to apply the framework that we designed to these use cases, trying to see and to show how it could be reused and why it is useful. Here you have two of the four examples. And if we look more in details, here is the occupancy sensor result, and here is the smartwatch result. This thing is what we call the Iot Hardware Profile. So you can see for every block what level of specification has been used for the model here and here. And we see graphically that it is quite different. And on the left, on the right, sorry, what you see is the related carbon footprint for each block. So it is interesting for two things. The first one is getting a value, an approximation of the footprint for the IoT device that you are interested in. And the second one is to understand where are the hotspots. It means we would like to know which are the blocks in the IoT hardware profiles that have the highest impact. And here it's quite interesting also to see that for the occupancy sensor, yes, electronics has an impact, but it's almost at the same level than casing and transport. So electronic is not the first hotspot for this small IoT device, whereas in the smartwatch, we see that memories ICs and processing ICs are way more impactful. And so we really acknowledge there that the hotspot depends on the hardware profile, obviously, but importantly, that all IoT devices are not equal. I see in the chat a question, why do you focus on the carbon footprint? Isn't the mineral, metal, petrol, and the footprint of other scarce resources more impactful, critical? That's a very interesting question. If you do agree, we will maybe target that a bit later because I will come up on this. But this is a very important question. We know indeed that there are some limitations, and it's also a bit related to the comment that has just been done by Danny in the chat, which is actually the third point here. We only focuses on the production and a single indicator. So it's not sufficient, but it's a first step. And I would say also that the complexity is such that everything couldn't be covered at once. So we had to start somewhere, and we start with this indicator only for production. But this study is something that we did almost 6 months or 1 year ago, and now we are indeed working on something else. And the second example will detail this more into details. But another limitation that is worth to be mentioned is the fact that we compare the result of our framework with some results that are available mainly from Google and Apple, for example, for the Google Home Mini and smartwatches. And what we can see is that the result obtained in the framework, so it's a log scale, do not always fit the result provided by Google and Apple. So it's usually underestimated. And this could be explained by two things. The first one is the truncation error. This is something that is really well known in the LCA community. It means that when you model the environmental impacts of devices with a bottom-up approach, so you really try to split each component, each process, and try to build up the impact that way. It is very likely that you underestimate the real impact because you cannot cover all the sub-processes and all the things that are happening down there. So this is one explanation. The second one is also that it obviously has been modeled a bit differently. But what is very difficult is that in LCA, and especially LCA for electronics, details are often not provided. You usually just have the result, which is very frustrating and really hinders the comparison and the understanding of the modeling. And this is the case for Google and Apple. You only have the final result, nothing about how it has been modeled. And the last point is that databases are usually not open source, which is also an issue that we can discuss later on. But all the values that we provided for the framework, that we obtained for the framework, are all provided in the paper. Then when we finish that framework and apply it on use case, etc., we wanted to ask a second question, which is this one: how coherent is the massive deployment of devices with the Paris Agreement objectives? And this might relate to your question in the chat, Danny, why we choose the carbon footprint. Actually, we choose the carbon footprint also because it's one of the only indicator for which we have specific targets a long time for reduction, at least trying to target path regarding indicators. So what we try to do is first try to gather all the studies or reports that were projecting a number of IoT device, a massive deployment of IoT device, report this and try to see how they compare with each other. So we saw, as I shown you at the beginning of the presentation, Cisco is at the very bottom, and others trends are showing upward trends that are in higher values. And what we decided is, okay, we cannot capture all of them, so let's take two trends that are kind of capturing how the trends are predicted to improve. So we choose to focus on Cisco trend and the Statista one, so the green and the red trend that is there. And so this fixed the number of devices that we consider for the 10 next years, 10 upcoming years. And then we try to leverage our framework to take the lowest range of the framework and try to define a simple hardware profile, average simple hardware profile for IoT devices with its carbon footprint, related carbon footprint, and do the same for the upper value of the framework, and therefore defining what we call a more complex hardware profile, which we call the average carbon footprint of complex profile. So very basic modeling, and then we just use one parameter, which is the share between the simple and the complex devices. Okay, we know that this modeling has some limits, but the idea is really to keep something simple and try to understand where it brings us. And so when we do this modeling, what we obtain is the three graphs on the right. So I know it's a bit crowded, but here we want to get the sense out of it. So let's decompose it. For the green and red lines, it's exactly the same methodology that has been applied. It's just related to one or the other trends that we consider. And so the goal here is trying to put in perspective how the footprint will evolve if we consider three scenarios. One where simple hardware devices are the most present. So it's like 90% of simple hardware profiles. And the more we are going on the right, the more the hardware profiles become significant, and we have up to 90% of complex hardware profile on the right. And what we see is that apart from the absolute numbers that basically ranges from 22 megaton CO2 equivalent to 1,000 roughly megaton CO2 equivalent, what we see is that saying that means basically, okay, it could range from nearly nothing to a huge increase of the carbon footprint. So the message is not just the absolute value, is really on the scenario that are shown here. It means that deploying IoT is not in itself problematic. The problem is in how we are going to develop and deploy IoT devices. The more complex we get, the more likely it is going to be a high footprint. The advantage here is that we try to quantify, and then we put that in perspective with the pathway that we should follow if we are coherent with Paris Agreement targets. So this line means that in 2020, we have taken the production only, as we are targeting only production here, the production part of ICT in CO2 equivalent. And then we applied the decreasing of like 7 or 8% a year to reach the objective of Paris Agreement. And so it shows the trend that we should follow for the whole ICT production, not IoT, whole ICT production. It shows the trend that we should follow. And here we show the trend, depending on the scenario, related to the deployment, production and deployment of the IoT device, massive IoT device. And so yeah, that's really the point that I wanted to make. We have here really top-down roadmap, I could say, and the result that we provided with the framework are much more bottom-up, but it's bringing the two together that are interesting. And here, the 2 points that you see there is to the best of our knowledge, the two only studies that have tried to quantify the environmental impacts of IoT. So we see that one is really high, the other one was in 2015 and was more in the range here provided for the Statista one. But still, it means that the trends are something really important to acknowledge. This is done for the first part. I don't know if someone wants to ask questions so far, or if it's better that I keep going and keep a bit of time for the end. I don't know how you feel about that.
I do have a few questions, but I'm happy to take them all together at the end, so maybe just move on.
Okay. I will be a bit quicker on this point so that we have a bit of time at the end. Now, what I'm going to talk about is a life cycle assessment for wireless power transfer. So what we did is actually, we go back to this small figure. Now it's still focusing on the IoT part, but this time we try to include the whole life cycle and not only carbon footprint, but 4 indicators. Here, the main question was, how does a state-of-the-art wireless power transfer system compare to a battery-powered system in terms of environmental impacts? And so just for you to picture what is this question about, on the right, you have that small system, which is basically a conventional wireless node, on which we put on top an energy harvesting system that allows it to recover RF energy to supply the nodes rather than a battery. And so our question was like, how does this compare one to the other? Again, it's going, first phase is like really defining what we include, what are the assumptions, etc. Then we model in the LCA modeling tool. and then we have results. And the conclusion of this, so now we have, it's, I would not say it's not related to the framework that we did before, but here it's much more specific. We really carried out this LCA while being very specific on all the components, and it's very dependent on the system that we have in front of us. So much more specific than the framework we saw before. Here you have the 4 indicators. And what we acknowledge at the end is that the environmental impacts of the wireless power transfer solution was higher than the coin cell solution. A lifetime of 10 years was assumed. And the gap is from like 5 to 7 times. It's quite interesting to go deeper in the result, because we saw at that point that the production and the use phase were kind of half-half responsible for this footprint, even though in the wireless power transfer, we see that the production and the use of the system that can send the energy through the air to power the node wirelessly is the main contributor. So it's mainly, and it's also about physics, like the further you are and the propagation of the energy is just dissipating, and so you need to send more energy from the base station. But here it's quite interesting to be able to compare it with the solution which includes a battery. Because we often say that battery are the problem, or at least one problem. It really depends on what power consumption is needed, the lifetime, and the modeling. But here, it's really putting forward that the wireless power transfer system is more impactful. However, we only consider one base station and one sensor node. And we also carried out the same study if we put more nodes, so more smart sensors, in the system. And what we see is that now the axes are broken here. The use phase is really dominating a lot, more than 60% for almost all indicators, is really dominating the impact. And so this obviously wireless power transfer can in some very specific use case be needed, and we cannot do without it. But the point here is to say that if we have to choose between the wireless power transfer and a coin cell battery for this type of application, it does not make sense to go for wireless power transfer. And this is also important to underline in the context of smart homes and a lot of things that tend to show a trend to be like powered wirelessly. This raises questions in terms of sustainability issue. Okay, and so we reached the conclusions. The question of the talk was why do we need life cycle thinking in the context of IoT? And I would conclude with a few points, which is that IoT is a fast-growing subpart of ICT, which implies a massive deployment of electronics. And we know that indeed electronics have environmental impacts that are not only carbon footprint, as you mentioned, Danny, but this must be better understood for the IoT. There is also a high degree of heterogeneity in IoT devices, and so it is very important to keep in mind that all IoT devices are not equal, and we cannot swap one with the other, and the environmental impacts of one are not the one of the others. And to conclude also, LCA of electronics also embed a lot of limitation and blind spots. We are aware of that. And the current modeling of electronics, of environmental impacts of electronics, are just a downgraded pictures of the reality. It's better than nothing, but it is just what it is. More expertise is definitely needed on this topic. And as you mentioned, Danny, carbon footprint is only one dark side. There is also all the problems related with like the management of the waste, electronic waste, which is also a very important problem in the context of IoT. And it's almost done on my side. I don't know if we have a few IoT designers here, but yeah, if so, there is also a small take-home messages down there. I'm done. So if you have any question or discussion or whatever, it's more than open. I will skip the last slide. Thanks a lot.
Thank you, Thibault.